In the late 19th century, scientists were studying a natural phenomenon called blackbody radiation that occurs when metal is heated. When the metal reaches a certain temperature, it starts emitting electromagnetic radiation in the form of heat and light. Scientists measured the intensity of the light as a function of the wavelength and temperature in an attempt to quantify a mathematical relationship. Since the newly developed models seemed to work well within the visible light range, scientists attempted to apply the classical mechanics Newton had discovered centuries earlier. This type of mechanics, that assumed energy was a gradual quantity, could not predict the radiation emitted from the blackbody at all temperatures. In fact, this model predicted that any hot object could emit devastating ultraviolet rays, X-rays, and even gamma rays. To account for this observation, Max Planck proposed that the exchange of energy between matter and radiation occurs in quanta, or discrete energy packets, hence the name, quantum mechanics. To prove the idea that energy transfers occurred in quanta, Planck conducted experiments where different wavelengths of radiation were directed at a plate of metal. Conclusions from this experiment defied classical Newtonian mechanics. Firstly, electrons were ejected from the metal only when certain wavelengths of light hit the surface. Secondly, the intensity of the light didn't seem to matter. Only the wavelength determined whether an electron could escape. Thirdly, the kinetic energy of the ejected electron increased linearly with the frequency of light. When any wavelength of light is passed through a double slit, it experiences a diffraction pattern, like the one shown here. Certain areas have more intense light than others, and nodes, areas with complete destructive interference, appear in between the light areas. When particles are passed through a double slit, they go straight through, without any evidence of wave behavior. While studying electrons, scientists discovered something rather curious. Electrons behave both like particles and waves. Since electrons behave like waves, we can model them with something known as the wave equation. The German physicist Werner Heisenberg proposed that the dual nature of matter places a fundamental limitation on how precisely we can know both the location and the momentum of an object at any given instant. This limitation only becomes important when we consider matter at the subatomic level. That means electrons, protons, and neutrons. This is called the Heisenberg uncertainty principle. Erwin Schrödinger pursued the idea of subatomic particles behaving like waves, because to him, the electron bound to the nucleus seemed like a standing wave. Schrödinger and de Broglie began to do research on the wave mechanical description of the atom. Basically, Schrödinger's equation is a wave function, often labeled with the Greek letter psi, which is a function that describes the 3D coordinates of an electron. This wave function can have a variety of different operators applied to it. The square of the wave function indicates the probability of finding an electron near a particular point in space. This is most conveniently represented as a probability distribution, in which the intensity of color is used to indicate the probability value near a given point in space. The visual that it produces is sometimes called an electron density map, an electron density, an electron probability, or an atomic orbital. All of those terms can be used almost interchangeably.